Stars are the lifeblood of the universe, lighting up the cosmos and playing a crucial role in shaping everything we know. Stars are not just distant lights in the sky. They are the forges where elements are created, from hydrogen and helium to the heavier elements that make up planets and life itself. Stars are the architects of the universe. Today, we're diving into the fascinating life cycle of stars, from their dramatic births to their extraordinary deaths, and how they shape everything around us. Stars begin their lives in massive clouds of gas and dust, called molecular clouds or stellar nurseries. These regions are cold, dense, and rich in hydrogen. Molecular clouds are often hundreds of light years across and contain enough material to form thousands of stars. Over time, gravity causes parts of the cloud to collapse into clumps, forming what's known as a protostar. This process can take millions of years. As the protostar grows denser, the pressure and temperature increase, igniting nuclear fusion, the process where hydrogen atoms fuse into helium, releasing tremendous energy. This marks the beginning of the main sequence phase of a star's life. At this moment, a star is officially born. The newly formed star will continue to shine for millions to billions of years, depending on its mass. The journey from a molecular cloud to a main sequence star involves several stages, including the formation of a protostar, the ignition of nuclear fusion, and the stabilization of the star's core. In the core of the star, nuclear fusion reactions continue to convert hydrogen into helium, producing the light and heat that we see and feel. Young star clusters often contain stars at various stages of formation, providing a glimpse into the dynamic and ongoing process of starbirth. These star-forming regions are some of the most beautiful and dynamic places in the universe, with vibrant colors and swirling gases creating a cosmic dance of creation. Our own Milky Way galaxy is home to numerous star-forming regions, each contributing to the ongoing cycle of stellar birth and evolution. The majority of a star's life is spent in the main sequence phase, where it steadily burns hydrogen in its core. The size of the star determines how long it stays in this phase. Smaller stars, like red dwarfs, burn their fuel slowly, lasting billions of years, while massive stars burn brightly and live for only a few million years. Our Sun, a yellow dwarf, is also in the main sequence phase, burning hydrogen steadily. During this phase, nuclear fusion in the core converts hydrogen into helium, releasing energy. Blue giants, much larger than our Sun, have shorter lifespans due to their rapid fuel consumption. Star clusters often contain stars at various stages of the main sequence phase, showcasing their diversity. The main sequence phase is a period of stability, where stars maintain a balance between gravity and pressure. Stars also exhibit magnetic activity and solar flares during this phase, influencing their surroundings. By studying the light spectrum of stars, astronomers can determine their composition and age. Eventually, stars exhaust their hydrogen fuel and leave the main sequence phase, evolving into red giants or supergiants. As stars exhaust their hydrogen fuel, their fates diverge depending on their size. Low to medium mass stars like our Sun swell into red giants, expanding to engulf nearby planets. In their final stages, they shed their outer layers, creating a beautiful planetary nebula, leaving behind a dense, white dwarf, a stellar remnant that gradually cools over billions of years. The life cycle of these stars begins in stellar nurseries, where clouds of gas and dust collapse under gravity to form protostars. These protostars eventually ignite nuclear fusion, becoming main sequence stars that burn hydrogen in their cores for billions of years. As they age, they exhaust their hydrogen fuel and expand into red giants, a phase that can last for a few million years. During the red giant phase, they shed their outer layers, creating stunning planetary nebulae that light up the cosmos. The core that remains becomes a white dwarf, a dense remnant that will cool and fade over billions of years. marking the end of the star's life cycle. For massive stars, the story is far more explosive and dramatic. Once their cores are dominated by iron, fusion stops, and gravity takes over. The core contracts under its own weight, leading to a dramatic collapse. The star collapses inward, triggering a supernova, a cataclysmic explosion that can outshine entire galaxies. This explosion is one of the most energetic events in the universe. What's left behind depends on the star's original mass. The remnants of the supernova can be incredibly fascinating. If the remaining core is between about 1.4 and 3 times the mass of our Sun, it might form a neutron star, an incredibly dense object. Neutron stars are so dense that a sugar cube-sized amount of their material would weigh about 1 billion tons on Earth. If the core is even more massive, it can collapse further to form a black hole, where gravity is so strong that not even light can escape. Black holes are regions of space-time exhibiting such strong gravitational effects that nothing, not even particles and electromagnetic radiation such as light, can escape from inside it. Neutron stars can also become pulsars, emitting beams of radiation that sweep through space like lighthouse beams. These beams can be detected as pulses of radio waves, X-rays, or even gamma rays. Black holes, on the other hand, can have accretion disks of material spiraling into them, heating up and emitting X-rays. These phenomena make black holes some of the most mysterious and intriguing objects in the cosmos. The fate of massive stars is a testament to the incredible forces at play in the universe, shaping the cosmos in ways that continue to astound and inspire us. Interestingly, the elements created during a star's death, like carbon, oxygen, and iron, are scattered across the universe, becoming the building blocks for new stars, planets, and even life itself. These elements, forged in the intense heat and pressure of a star's core, are released into space when the star dies, often in a spectacular supernova explosion. Stars are more than just points of light in the night sky. They are the forges where the elements necessary for life are created. Without stars, there would be no carbon for our bodies, no oxygen for us to breathe, and no iron in our blood. They are cosmic engines, creating the elements that make up everything around us, including us. The process of nuclear fusion in stars not only powers them, but also produces the elements that form planets, moons, and all living organisms. Their births and deaths tell the story of how the universe evolves, reminding us of the interconnectedness of all things. The death of one star can trigger the birth of another, as the material it releases into space can coalesce to form new stars and planets. This cycle of birth, death, and rebirth is a fundamental aspect of the universe, illustrating the profound connection between all things. The elements scattered by dying stars mix with cosmic dust and gas, eventually coalescing into new stars and planetary systems. This ongoing process of star formation and destruction is a testament to the dynamic and ever-changing nature of the cosmos. In this grand cosmic dance, we see the interconnectedness of all things. From the smallest atom to the largest galaxy, everything is linked in a continuous cycle of creation and destruction. The story of stars is, in many ways, the story of the universe itself.